Welcome to Viz Math e-Pathshala. Today's topic is Lagrange's theorem and Cosets.
Okay. Okay. So in the last lecture, we have proved that suppose you have a group. Suppose you have a group G and H be a subgroup of G, right? Then you can decompose G in terms of left cosets, right? Left cosets of H in G, where A is the set of all representatives taken from each distinct left coset of H in G, right? What we have defined as the left coset decomposition of the group G with respect to a subgroup H. Okay, and this idea will lead to count the total number of elements of a group whenever we are considering finite groups, and eventually the number of elements of a finite group G will be equal to the sum of those in the cosets of a subgroup. So if G be finite, then you can write that the cardinality of G, the order of the group, is actually summation of H, summation of the cardinality of H where A belongs to capital A, right? That means now since G is finite, so since G is finite, since G is finite, so we can write so so there are finitely many left cosets of H in G, right? Suppose the left cosets are A1H, A2H, AKH, right? Which are the distinct left cosets of H in G. right? So whenever you are considering a group and a subgroup of G, and if the group is finite, then this group can be decomposed as a union of finitely many left cosets of H in G. Okay, and this is going to be so this will be, so the order of the group is actually cardinality of A1H plus cardinality of A2H plus cardinality of AKH, where A1H, A2H and AKH are the distinct left cosets of H in G, right? Now recall that in the last lecture we have proved that any left coset has the same cardinality with the cardinality of the subgroup H. Recall that the cardinality of any left coset equals with the cardinality of the subgroup H. And using this result, you can write down the above equation as, so from star we have, so the order of the group equals with cardinality of H plus cardinality of H up to k times, right? So this is k times of cardinality of H, and this equation indicates that the order of H divides order of G, right? Since we have written the order of G as a multiple of the order of H, the integral multiple of order of H, so that means order of H divides order of G. And this turns out to be an important theorem, which is called Lagrange's theorem, right? Right. So order of H divides order of G, and what is the quotient? The quotient is K, right? The quotient is K. And what is K? K is the number of distinct left cosets of H in G. Now one may ask that if we consider right cosets instead of left cosets, then what will happen? We will get the same thing as above, because we have also proved that the number of left cosets of a subgroup in a group G equals with the number of right cosets of that subgroup in the group G, right? So the cardinality of the set of all left cosets of H in G equals with the cardinality of the set of all right cosets of H in G. And this observation gives you the same thing here if you consider right coset instead of left cosets. So you will get the same number of distinct cosets actually, right? So the theorem is that if H be a subgroup of a finite group G, if H be a subgroup of a finite group G, then what we have seen is that the order of H divides the order of the group G, or the order of the group G, that is order of H divides order of G, right? Okay, so this is the theorem and the proof lies in the above discussion. The proof is the above discussion. Okay. So this is your task to write down the proof on your own in view of the above discussion. Okay. Okay. So note that. So if G be a finite group and H be a subgroup of G, then order of H divides order of G, and the quotient in this division is the number of distinct left cosets of H in G. Okay, number of distinct left cosets of H in G. That is, in other words, you can say that if you consider a finite group and a subgroup H of that group, then the number of distinct left cosets of H in G equals with order of G by order of H. Or in other words, the number of distinct left cosets of H in G equals with order of G by order of H. Okay. So, 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 yeah. Okay. So for finite groups and a subgroup of that group, you have you have proved that the number of distinct left cosets of H in G will be equal to order of G by order of H. So that is fine. Now the question is that, so in this proof you have seen that whenever you are considering finite groups, then you are getting that the number of distinct left cosets of a subgroup in that group is this. But in some infinite groups also, and the subgroups of that infinite groups, you will find that the number of left cosets of that subgroup in the group may be finite, although the cardinality of the groups are infinite. Okay, so remark is that uh, in some infinite groups and subgroups of those groups one may have finite number of distinct left cosets of that subgroup in the infinite group. Okay, that is given. Okay, for example, I have already deduced that for the case of, suppose you are considering yeah, for example, let us consider the group Z plus. So it is an infinite group, right? And let H is 6Z. Suppose you are considering 6Z. So this is also an infinite subgroup of the infinite group Z plus. But the number of left cosets of Z of 6Z in Z plus, but we have seen that the complete set of distinct left cosets of 6Z in Z plus is, what are the left cosets? That is, the first one is 0 plus 6Z, right? 1 plus 6Z, 2 plus 6Z, 3 plus 6Z, 4 plus 6Z, and 5 plus 6Z, right? So how many elements does this set have? This set has, so we have noticed 6 distinct left cosets of h equal to 6Z in Z plus, right? So in spite of the fact that the group is infinite and the subgroup is infinite, although you are getting finite number of distinct left cosets, right? So that means for infinite groups also you may have finite number of left cosets of a subgroup of an infinite subgroup of an infinite group T. Right? So these are very familiar examples you have on your hand, right? And with respect to this observation, we are tempting to define in general the number of the cardinality of the set of all left cosets of a subgroup H in a given group G as a determining factor to characterize the groups. What is that? The definition is that suppose you have a group, any group, okay, let G be a group, and H be a subgroup of G. Okay, so you are considering any group. It is it may be finite, it may be infinite, whatever it is, and even considering one subgroup of this group. Then we are defining that the cardinality of the set of all distinct left cosets of H in G is defined to be the index of the subgroup H in the group G. Okay, so it is defined to be the index of the subgroup. Okay, is defined to be the index of the subgroup H in the group G, and we denote it by this third bracket G colon H. Okay, so in terms of this definition, we have seen that by Lagrange's theorem, for a finite group G and a subgroup H of G, the index G colon H is finite and equals with this is the order of the group by order of H. Okay, and in the above example, so in the group Z plus and for a subgroup H equal to NZ, you can deduce that the index of the subgroup NZ is so Z colon NZ, it is actually N. Okay, fine. Yeah, and also in the group S3, that is E phi psi psi square phi psi, where phi is 1 2, psi is 1 2 3. Okay, and E is the identity permutation. Then the index of the subgroup H equal to E phi is, it has been calculated that we have 3 distinct left cosets. Okay, if you go back to the discussion made in our lecture 10 or 11 maybe, so you will see that the number of distinct left cosets of this subgroup in the symmetric group over 3s3 is 3, right? So the index of this subgroup, so s3 colon h, it was 3. And in view of Lagrange's theorem, we have seen that the order of the group S3 is, so it is actually this, that is 6 by 2, so it is 3. Okay. So let us consider the group R plus and the subgroup Z in this group. Okay. Then the problem is that you need to show that, prove that, so this is your exercise, prove that you can set up a bisection. One may define a bijection, a bijective map between the set of all distinct left cosets of Z in the group R one may define a bisection between the set of all distinct left cosets of Z in R and the set semi closed 0 1 open interval. Yeah, so this is your exercise complete. Okay. 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 Now another, so one corollary of Lagrange's theorem is that, so let G be a finite group. So let G be a finite group. So actually using Lagrange's theorem, you can make a guess about the order of the elements of the group, right? Okay, so let us see that let G be a finite group and A belongs to G, be any element. Okay, take any element of that group. Then you can show that order of the element A, it divides the order of the group. Okay, so that is an interesting fact, and using this you can have a guess of what would be the order of the element, what are the possibilities of the order of the element. So you will have using this criteria. And what is the proof of this? So yeah, so proof lies in the fact that whenever you are considering a finite group, any group, whether it is finite or infinite, and given any non-identity element, you can define a cyclic subgroup, right? Now if that, now the group is itself a finite group, so the cyclic subgroup constructed upon this element will also be finite, right? And not only that, since it is a finite cyclic group, so the order of that subgroup equals with the order of the element, right? We have proved that the order of the cyclic subgroup constructed using A generated by A is actually equal to the order of the group. Okay, and using this fact and Lagrange's theorem, you have this result, because by Lagrange's theorem, order of that subgroup will divide the order of the group, and since the order of the subgroup equals with the order of the element, so order of the element will divide the order of the group. So that is the scheme of the proof. Okay, okay. So yeah. So I think yeah. Since order of G is finite, then there exists n comma m belongs to Z such that a to the power n must be equal to a to the power m, because the order of the group is finite. So whenever you are generating the cyclic subgroup by A, that you are getting elements like a to the power n for n belongs to Z. Now since the number of elements of the group is finite, so the number of elements of that subgroup will also be finite. That means after some steps, a to the power n will coincide with some a to the power m. So elements will be equal with each other, right? So that means, and this observation gives you the fact that, so a to the power, suppose n is greater than m, so that n greater than m, a to the power m, n equal to a to the power m. So that means a to the power n minus m equal to identity. And this fact tells you that order of A is finite, right? So you can define the least integer, positive integer, for which a to the power k is identity, and that is defined to be the order of the element. So order of A is finite. Okay, now it is fine. Okay, now using this element, now if H is the cyclic subgroup L angle R angle A, then order of H equal to the order of the element A. So hence, by using Lagrange's theorem, order of H divides order of G. That is, since order of H is order of A, so order of A divides order of G. Okay, fine. So this completes the proof. And using this fact, you can write down another corollary, that in a finite group, G, a to the power order of G must be equal to identity for all A belongs to G. Okay. Now since order of G is the multiple of order of A, and a to the power order of A is identity, so if you compose it up to order of G times, then it will give you the identity, right? Okay, I just left this as an exercise. You just complete the proof. Okay, fine. Okay, another important corollary is that and it is concerned with the cyclic groups of prime order. It is concerned with the group of order prime. right? Suppose you have a group G of order 7, then you will see that this group must be a cyclic group. Okay, so what is the proof? So suppose G be a group of prime order. Okay, say P, then G must be cyclic. Every group of order prime is cyclic. Okay, so what is the proof? So let order of G is P a prime number. Okay, now consider, now since this group is of prime order, so it must have at least two elements. One is identity and another one is non-identity. At least two elements, right? So consider one non-identity element A belongs to G. Okay, now using the above corollary, so order of A divides the order of G, but this is a prime number. So whenever one integer divides, positive integer divides a prime, that, so using the definition of a prime, so you must have, so thus order of A is either 1 or P, since P being a prime, right? Okay, now since the element, since A is non-identity, so this says that order of A must be P, right? So therefore, so now using this non-identity element A, the cyclic subgroup L angle R angle A generated by A is obviously a subset of G, right? It is a subgroup of G. And you have seen that this equals with the, and you have seen that order of this subgroup is equal to order of A, that means P, and it is equal to the order of the group G. Now since the groups G and the cyclic subgroup generated by A, so since the group G is finite, and since the cyclic subgroup generated by A is a subset of G, having the property that their orders are same, so that means, so being a finite set, you must conclude that G equals with the cyclic subgroup generated by A. That is, G is a cyclic group generated by A. What is A? A is a non-identity element of the group. So in this, so if you look at the proof, you will see that apart from having a cyclic group, you can actually have another more important feature of this aspect, is that any non-identity element of that group of prime order is a generator of the group. Take any non-identity element, this will generate the group if the order of the group is prime. So that is an important fact. Okay. Yeah. Okay. এই জায়গাটা বোঝা যাচ্ছে তো যেটা বলছি? বোঝা গেছে প্রমাণটা? হ্যালো, শোনা যাচ্ছে না নাকি? হ্যালো
শোনা যাচ্ছে।
হ্যালো,
শোনা যাচ্ছে স্যার।
বলছি বোঝা যাচ্ছে তো?
হ্যাঁ স্যার।
না, শোনা যাচ্ছে, বলছি বোঝা যাচ্ছে তো?
হ্যাঁ স্যার।
আচ্ছা আচ্ছা, ঠিক আছে ঠিক আছে। ওকে, fine. Now, using Lagrange's theorem, we can deduce a few important results which are related to the theory of numbers. Okay, and for this, let us recall that for any n greater than 0, for any integer n, recall that for any positive integer n, we can define phi n to be the number of positive integers that are less than n that are less than n and relatively prime to n. Right? Called the Euler's phi function, right? Phi function. Okay. Okay. And with respect to this definition, we can state one important theorem in the theory of numbers, which is known as Euler's theorem. And what does it state? It states that let n be a positive integer then a to the power phi n is congruent to 1 mod n. What is a? Where a is relatively prime to, where a is an integer relatively prime to n. Okay, and phi is the Euler's phi function. So that means let n be a positive for any positive integer n. If it is just whenever once you assume it is fixed. So for this n, and take any integer a which is relatively prime to n, then a to the power phi n, then it leaves remainder 1 whenever you are dividing it by n. Okay, and suppose you have if you consider n to be 1, then this is very trivial, right? Okay. So proof is that if n is 1, then it is obvious. So suppose that n is greater than 1. Okay, n is greater than 1. Okay, now consider the set x equal to 1, 2, 3, n minus 1. Okay, right? Now this set x turns out to be a monoid, then this set x turns out to be a monoid with respect to the multiplication modulo n, right? Right? Actually, we have proved that. We have proved this fact in our earlier discussion, right? That this set forms a monoid with respect to multiplication modulo n. Okay, right? And amongst these elements, some elements will be invertible. And what are those? The elements which are relatively prime to n, right? So recall that an element k in x is invertible if and only if GCD of k comma n is 1, right? And using this fact, if you take, so suppose G be the set of all those invertible elements. So the set of all invertible elements in x dot. Okay, fine. The monoid with respect to the multiplication modulo n. That is, G consists of those k belongs to Z plus which are less than n, and GCD of k comma n is 1, right? And we have proved that in our earlier discussions that this is the group of units, right? So G forms a group with respect to dot induced on x, right? It is the multiplication modulo n. Okay, and this group, the order of the group, and observe that the order of the group is actually the image of the Euler's phi function at the point n. Okay, now let small a be any integer that is relatively prime to n. Okay, so then what we do now, we need to recall the division algorithm. And we do remember that whenever this type of situation occurs, we are inviting this division algorithm. Suppose you have an integer a and a positive integer n, then using this division algorithm, you will get some exciting facts, right? So using division algorithm, you will get one quotient and one remainder. We can represent a as a equal to nq plus r, where where q and r are integers, and this r has some fascinating properties. This, so this r lies in between 0 and n. Okay, now we need to recall that. Now note that GCD of a comma n, it has been assumed to be 1. So if the GCD of a comma n is assumed to be 1, then by the use of Euclidean algorithm, so this is actually GCD of r comma n, and this implies that r must be greater than 0. Therefore, this r is actually in the group G, right? Now, what is a to the power phi n? So it is actually, so a is nq plus r to the power phi n, right? Right? So now, what will happen? What will happen? Then, so this is going to be, so this is an integer. So nq plus r to the power some integer. So take the expansion and you will get that each term is a multiple of n. So just accumulating all those terms except the last one. Then accumulating all those terms and take the sum, then you will get one integer which is a multiple of n. That means it is some q star n plus the last term will be r to the power phi n, right? Okay. So for some q star belongs to z. So that means, now what is phi n? Phi n is the order of the group G. So this is q star n plus r to the power order of G. Now since this r is in the group G, so using Lagrange's theorem, so r to the power order of G must be equal to the identity of the group G. So what is the identity of the group G? Which is 1. So that means, so it is, so that means it is q star n, so it is congruent to plus 1, right? So yeah, sorry, 1 minute. So if you take the modulo, then it is actually 1. Yes, modulo n. Okay, so this completes the proof of the theorem.